Good morning. My name is Charles Fan, and I'm the co-founder and CEO of MemVerge. My talk title for today is Persistent Memory plus Data Services equal to Big Memory. It is to share the big memory software that we have been developing over the last 3 years and some of the use cases that we have tried with some of your customers. Okay, let me get started. Yeah, so MemVerge is a software startup company. We started about 3 years ago. And the reason we started this company, number one, is because of the need that we see from the customers to handle real-time data. So you see a chart here, and this is from IDC. The numbers there, the orange bar is not surprising. That's just indicating the exponential growth of data that will be continuing in the coming years. And what is a bit of surprising is a blue line, and that is the percentage of real-time data as a percentage of the overall data. And that is also growing in the next few years. By 2024, it is projected to reach close to 25%, meaning close to a quarter of the world's data will be real-time data. That drives the demand for a memory-centric infrastructure. The reason is to deal with real-time data, you need to have a low latency in order to have either insights or even actions within microseconds. Storage system will be too slow for that. So typically a real-time application requires the data to be placed in memory for it to run well. And that's actually happening already. If we look at real-time data analytics or artificial intelligence, machine learning, more and more the software frameworks are based on memory. And DRAM today is the primary memory resource that those software framework uses. And DRAM is limited in its capacity. You typically have a few hundred gigabytes, and it becomes very expensive when you start to have terabytes level of DRAM in a server system. And it is also relatively costly. So there has been demand for a new type of memory to answer to the need of growing real-time data and real-time applications. The good news is that new memory types are coming. In fact, the first of its kind is already here in the form of Optane persistent memory released by Intel last year. Optane persistent memory is based on a technology called 3D XPoint, and that is just one of the technologies in the so-called persistent memory or storage class memory field. And there are other technologies also emerging, and we do expect there should be multiple vendors offering the technology by the year of 2022. And the chart on the left is also from IDC. It is really projecting a very fast growth of this new type of memory over the next few years to reach $2.6 billion by 2023. And that is a growth percentage of 248%, very significant growth. And obviously last year was the first year this technology was selling, and Intel was the only vendor delivering it. And this will be the case probably for the next couple of years. But we will be seeing the second, the third, and maybe the fourth vendors introducing alternative technologies to deliver the benefits of persistent memory. So what are the benefits? Number one, capacity-wise, it is denser and bigger than DRAM. With Optane, you can have up to 6 terabytes in a 2-socket server today. And combined with DRAM, you can have to 9 terabytes of memory inside of a system. And this is expected to continue to grow in the overall capacity. The second benefit is cost. Obtained memory currently is at about half the price as DRAM for similar capacities. And this gap is also expected to widen as time goes along and as the density of persistent memory continue to grow, the per gigabyte price is expected to drop. And thirdly, perhaps most interestingly, this memory is persistent. As the memory becomes bigger, actually availability of that memory becomes more important because most of the data will be placed in that memory, and typically you don't have time to save it to the storage system or to hard drives or SSDs. Therefore, if you do have a failure, if you don't have persistence, then you lose all of the data that's in the memory, which will be ranging in the order of magnitude of terabytes, and that's very time consuming to recover or reconstruct. So if you have persistence in the underlying media, then it is possible to building high availability features into memory to allow the big memory applications to be crash resilient. So persistent memory at least provide these three benefits. It's bigger, it's cheaper, and it is persistent. And so in some ways, it is the right solution to address this demand from real-time applications. But today, if we just have these two, the customer demand and this particular hardware, there are still some gaps. And this gap is something a new layer of software can help bridge. What are the gaps? First is the compatibility with the existing applications. If the application is to take advantage of the obtained memory in its memory speed as memory, as a byte-addressable random access memory, but at the same time would like to enjoy the high availability provided by persistence, it's difficult to do today if you just have this hardware. You either have to change your application to program into the new API to enjoy both persistence and byte-addressability of this new memory media, or you have to give up one of them. You have to run in one of the compatibility modes, either the memory mode without enjoying the persistence, or storage mode without enjoying the byte addressability. So it's difficult to have the best of both worlds without the help of another layer of software. And fortunately, that layer of software is being developed, and it is what we call the big memory software. It essentially provides the compatibility with existing applications without rewriting. At the same time, it delivers the high capacity of the persistent memory in combination with the DRAM that's available there today. It bridges the performance gap. Persistent memory, with all of its benefits, it's bigger, cheaper, and persistent. It does have some drawbacks. It is a bit slower in latency, especially in writes, than the DRAM memory. So is there a way for the software to optimize the persistent memory to get performance close or at the DRAM performance? And this is something software could help, and I'll go into it. And thirdly, how can you deliver the high availability based on the persistence capability of the memory? And that is not as straightforward as we think, especially if you don't want to change the application. So those are really the value add this new layer of big memory software could provide. It provides compatibility with your existing application, provides better performance for high availability, provides larger memory capacity, all at the same time. And this is what MemVerge, my company, have been working on over the last 3+ years. And the rest of the talk, I'll go into exactly what technology did we build and how can it be used for the various use cases that our customers have. So the product that we deliver, in fact, we are delivering it this month to be generally available. And it is a product called Memory Machine. MemVerge memory machine. It is the world's first big memory software. And it is a software-only product. It is a subscription pricing model and can be deployed both on-prem and in the cloud. There are two versions of this product, and they actually map very well to the two important inventions or technologies that we created. The base version, we call standard edition, is a memory virtualization layer of software, as you can see from the picture on the right. It virtualizes DRAM and PMEM and make it available to the applications in a DRAM compatible API. And this way, the application does not need to change, and they can use this memory as a software-defined memory. So essentially, we sort of, for each application and each process, we would create a memory pool that is some ratio between PMEM and DRAM. And this ratio is dynamically configurable. And it provides in a DRAM compatible API that the application, either homegrown or third party, can just work as is. The benefit of this software-defined memory are threefold. The first is that it exposes or even amplifies the benefits of the underlying persistent memory. It is bigger, it is lower cost, and it is almost as performant as a DRAM. And the last part is enabled by the software optimization we have in memory machine that tiers between DRAM and PMEM. And we also have optimized memory allocation module that can have higher performance than what's provided in the kernel. And in order to achieve performance that is near or at the DRAM performance. And we can do all of this in a application compatible way without the application being changed. So that's the standard edition. It's a software-defined memory that provides this memory service in a software-defined way. And one last benefit of the standard service is that because it's software-defined, it can have different configuration for different applications that are running on the same server. So you can have different ratio between DRAM and PMEM. You can monitor their usage of memory, and you can achieve better SLAs for each of the application and without running into the noisy neighbor problem. So this is, in a way, providing a software-defined memory pool individually tailor-made for each of the applications. So number one, the software-defined memory provided by our standard edition. The second technology that we invented, and this is on top of this software-defined memory, is what we call a zero IO snapshot technology. And this allows you to capture the running state of an application and immediately save them on the persistent memory. In a way, it is similar to checkpointing, if you're familiar with the concept, which is popular in high-performance computing and other environments. With checkpointing, you're capturing the running application state, and then you move them to a storage system to save it. And when you need to recover it, you move them back from storage into memory, and you can restart the application from that instance. What we do in Zero IO Snapshot is similar to that, except we do not actually incur the data movement. We don't need to move the data from memory to storage, given the memory itself is now persistent. Our software-defined memory service, in order to be compatible with DRAM, is volatile. But this snapshot service can be enabled from our administrative GUI, that as an administrator, you can decide when and how and schedule it, the application state to be saved right in place on the persistent memory. And those snapshots is something you can roll your application back at any time. And it's also something after crash, you can go back to the closest or the most recent snapshot and restart the application from that point. And if you do have some logs, that you can replace the remaining log to recover all the way to the crash point. So this is a very innovative in-memory snapshot capability. And we not only allow you to take one snapshot, we allow you to take multiple snapshots repeatedly. And in doing that, we actually do not save the entire memory state, but we only lock down or track the deltas, the changed memory pages, and do the snapshot in that way. So it is conceptually similar to storage snapshot, where you use a mechanism called copy on write to manage the blocks of a storage system. Well, we are applying the same concept to memory and using those to managing the checkpoints of the application by tracking only the pages that has been changed. So this can be very efficient in both space and time. It can be efficient in the memory space that you occupy. It can also be efficient in terms of how fast the snapshot can be taken, and therefore less disruptive to the running applications. There can be a number of very interesting applications that can be built on top of this snapshot. And I listed a few here. You can have a time machine rolling back your applications. If you accidentally may have a user error that corrupted a database that's in memory, you can roll back to the snapshot that's before such a corruption occurred. You can also crash recover. So if you crash your server, and if you had regularly taken snapshot, similar to an autosave feature when you're editing a Word document, when the system recovers, you'll automatically go back to the last known good copy, which is the last snapshot that you have taken. And the most interesting use case, perhaps, on top of snapshot is what we call the instant cloning. So you can create a new memory space, new logical memory space, without actually replicating the physical memory. So because of this, you're creating new application instances with new logical memory spaces, but that map to the same physical memory space. And our memory virtualization layer actually tracking all the differences. And this way, it's suppose you have a 100 gigabyte in-memory database, and for the reason of better load handling or some test dev use cases, some debugging, you want to create another instance or another 5 instances for that matter, you can instantly, within a second, create new clones of this database, and they'll be running completely independently, and yet unknown to them, they are actually sharing the physical memory space of that particular application. And that is enabled by our memory machine. So that's another use case that you can have on top of the memory virtualization and snapshot capability. So to summarize, memory machine is a software-defined product that virtualizes DRAM and PMAM, deliver a software-defined memory service that is capacious, that is lower cost, and that is performant. And so you can enjoy big memory without compromise. On top of that, we offer a zero IO snapshot capability that allow you to deliver various availability and agility features on top of our software-defined memory that was not possible before. And so this is a new invention that we believe can open up a whole bunch of possibilities of how the application can be deployed. So that's a memory machine. And now let me go into the use cases. We have been working with a number of customers. As I mentioned, we are GAing the product this month, but we have had the product in what we call the early access program, and we have about a dozen customer POCs ongoing. And particularly, there are three verticals, 3 industries who have been working with us. to apply memory machine and obtain memory to deliver certain values that's not possible with other solutions. The first of such are the cloud service providers, and they are delivering VM as a service to their customers. And it is paramount to save the cost per VM and increase the density of VMs on their physical infrastructure. And this allows them to have a more compelling business model to their customers. And so over the last few months, we've been working with some of these cloud service providers in using Optane to enlarge the memory footprint, lower the memory cost, and therefore lower the per VM cost. It's the same amount of memory is to be allocated, and increase the number of VMs per server if the size of memory was a bottleneck. And the results has been very compelling, and I'll share it later in some of the performance numbers we were able to achieve by launching those cloud VMs based on the hybrid software-defined memory that we deliver. So that was the first. The second are in the media and entertainment industry, with studios making animation movies, for example, that they have many creative artists working on rendering and interactive applications that are run mostly in memory for speed. And it's all good until it crashes. And when it crashes, it takes hours to recover, because typically the work in memory was not saved onto the storage, because that would be too slow. That would slow the artist down. But now if it's not saved on the persistent storage, when it crashes, if you do not have a memory machine solution, the recovery can take hours. Or the work previously from the beginning of the day typically is lost. It could take 1 hour, 2 hours, or even longer to recover. And not only it is a productivity loss in terms of time, but it is also an interruption to the creative artists that could take more than a few hours to recover, because your stream of thoughts and your creative flow would be disrupted and interrupted by such crashes. And what we are able to offer is based on our snapshot capability. We can have an autosave feature for these rendering and artistic software, so that when the crash happens, recovery can be much shorter, in a matter of seconds, that the artist can be back to work to be their creative best. So that's the second use case on the media and entertainment, on the high availability of memory to really increase the productivity and creativity of their artists. And that's certainly not the only vertical that can benefit from Snapshot. We have also worked with customers in financial sector. So that's a third sector, in particular the trading applications and capital markets that are demanding the performance of memory, while they want availability, such as what I described, with the Snapshot, it can deliver, but also they like to have agility, the quickness to be able to create copies of the database. And if you remember from the last slide, that's exactly how our cloning feature works and what we can enable there. So we can quickly creating clones, either for test dev purposes or for performance scale out purposes. And so with these three sectors are the early targets where we find customers embracing this new big memory concepts. So let me dive into each of them and give you some numbers for reference. The first use case, as I mentioned, is for the cloud service provider. It's actually this particular cloud service provider is using KVM as their hypervisor and provisioning new VMs to serve their customers. And our purpose here is to deliver larger amount of memory to this hypervisor at a performance similar to DRAM, so that they can increase the number of VMs they can create on the same server without compromise on performance. And so how do we do? It's actually surprisingly good. And this is one example of running MySQL databases in the VM that's provisioned by this cloud service provider's KVM hypervisor. And the green bar is a baseline. And this is our software, Optane, and not invoked. Purely DRAM running the hypervisor and MySQL inside of it using sysbench to benchmark the MySQL performance. We get about 47,000 QPS, query per second, and this is pretty good, and this is supposedly the best you can get because persistent memory is slower than DRAM. It would be unrealistic to expect that performance to be near, or not to mention exceed, the DRAM performance. So the 5 bars on the right are the performance using our memory machine software, virtualizing DRAM and PMEM. And by the way, this database is 40 gigabytes in size. And that, as I mentioned, with our software, it can have dynamic ratio between PMEM and DRAM. And in this case, we tried different ratios from 0 to 2 gigabytes, 4 gigabytes, 8 gigabytes, 16 gigabytes of DRAM. And they serve as a fast tier within our software, and PMEM serve as a slower tier. And we measure the output running the same test, sysbench on MySQL running inside of those VMs. When it's purely PMEM, understandably, it is 20-some% slower because PMEM has a slower latency. But as we increase the amount of DRAM, the performance gets closer and closer to DRAM performance until at 16 gigabytes, it actually has higher performance at 49,000 QPS than the baseline where it's DRAM only. And we were very pleased to see these results because this is counterintuitive. How can you be faster when the underlying, or at least part of the underlying media, is slower? The answer is through software optimization, through our advanced allocation algorithm that we believe are superior to what the operating system was providing, and our tiering algorithm and various optimization we applied to those algorithms, that we were able to achieve DRAM performance at the right ratio between DRAM and PMEM. So that's an example of the performance parity claim and how it can help the cloud service providers from adopting this solution. So that was the first one. Let me tell you the second one, which is the crash recovery. And in this case, it is actually for financial in-memory databases. I mentioned the animation case. This also applies to the financial cases, whether you're using a time series database like KX, KDB Plus, or Shakti, or you're using a key value store like Redis. You see what's in common between these apps, that they are all memory intensive. And when it's memory intensive, is a place where our software might add a good amount of value here. So this is for the traders and the quantitative analysts, and they like for this service to always be available. But it does crash from time to time. And when this database crashes, it's a long time to recover, because typically the last time they saved to the drive was last night after the market closed. And everything that happened today typically runs in memory without persisting, because persisting will slow it down. So, but now when it crashes, you have to replay the whole transaction log, which could be in the billions, from last night, and that will take hours to recover to the crash point. Where with the snapshot, that we were able to do that much faster. And so this is using a time series database, KDB Plus, and measuring the snapshot and restore performance. And as you see, the blue line was without us. They have to replay the log from the very beginning, where the two orange lines on the left-hand side are the time that we take the snapshot and time we recover the snapshot to the database. And you see, we are reducing from many minutes to a single second. So that's a dramatic improvement. And in some cases in here, it may not even have enough DRAM to do the job, but with the right software-defined memory like we provided, you can leverage the capacity of PMEM to achieve the higher capacity the application needs. So this will illustrate for the snapshot, the performance that we have in taking and restoring from the snapshot. All right, so the third use case is a cloning use case. This is based on the same snapshot algorithm, how you can create additional instances of the running application, and without actually physically replicating the memory and incur the cost both in the time it needed to create those instances as well as extra memory that was being used. And we can do so without incurring either overhead. So here are just some numbers to illustrate. So without us, and by the way, this is logarithmic scale, so every line is 10x. Without us, you can use, for some applications, there are some internal mechanisms. For example, with Redis, there is a mechanism called RDB that you can capture state, save them on drive, and recover it from drive and recover the database. And now the green bar and orange bar are what you see in the performance, either doing that on DRAM only or doing it on the Intel memory mode, which is a way of using PMEM and DRAM together. You'll see the performance is 174 seconds to 224 seconds. So it's a few minutes for you to actually recover this database back into operation. And with our software, in this case, it only takes 0.2 seconds for this to take place. So there is a 1,000 times improvement in the amount of time needed to recover from a snapshot. And this is useful for crash recovery, and this number is also useful for cloning when you need to create multiple copies. This can be done instantly, creating those additional instances. All right, so now let me go to use case number 4. So I have 2 more to go. So this is AI ML, and for many of the AI ML use cases, memory is increasingly become a bottleneck. And we have been working with a few customers on various AI ML use cases. And I'll give one example of how we can enlarge the memory available to the models and embeddings. And therefore, it doesn't need to go to the hard drives and improve the performance of the whole system. And this is for a facial recognition application. The graph on the left is showing the TPS, transaction per second, that you can achieve. In this case, the orange is with memory machine, where the dark purple is the original. Without us, how it is using between DRAM and running MongoDB on hard drives to be able to store all the data. And you can see we are about 4 times better than the baseline without us using DRAM plus Mongo, because we really solve this data bigger than memory problem, that we make the memory bigger so data does not overflow the memory system. And the advantage on the latency is even more pronounced. You see on the bar on the right, again, the dark color is the baseline using DRAM plus MongoDB, where the brown line or orange line is our performance. And it can be up to 100 to 1,000 times faster on the latency. And this is really important for AI ML inference, that you like to quickly recognize the face rather than wait for a long time. You also like to really handle the bandwidth, the throughput of the queries that's coming into the system. And this is where a big memory-based system really shines for AI ML use cases. Okay. And now let me go to my last use case, which is another financial use case in the pub sub. This is to quickly, using RDMA between the servers, replicate the memory change on one server to the other servers. So this can be done synchronously or asynchronously, depending on the requirement from the application. And we were able to achieve some very good results. In fact, our first paying customer is someone who took this as the very first use case. And the performance that we can achieve is outstanding. Essentially, you can publish, in this case, from 1 to 7 servers with 210 subscriber processes all happening at the same time. And the event flow are coming in at a pretty high rate, 100,000 messages per second. And we are asked to really distribute this from memory to memory to the other 7 servers. And the line here are the average. The average latency, you see it's somewhere between 2 point something to 3 point something microsecond. And this is comparing to hundreds of microseconds or even milliseconds if you use a storage system to do such pub/sub. So it's a couple orders of improvement on this memory-based pub/sub system. And the bar here are showing the 99.9% tail latency. And this is to demonstrate the variance is relatively small. The laggard is within twice the latency of the average. And that is a desired property of these customers as well. So essentially we create a very low latency, high throughput pub/sub system, allow messages to be to permeate through the cluster in the memories. And this can also allow the capability of doing synchronous write with HA, so that what you write to memory can be protected before this can acknowledge to the application. So we can support both modes, the asynchronous mode and the synchronous mode, taking advantage of the memory as well as the fast network interconnect. Okay, so this is the last use case here. So the last 5 different use cases were just an illustration what a big memory system can enable in a customer environment. So to summarize, if you look at through those 5 use cases, that we're delivering scalability, we are delivering availability, we're delivering agility through the cloning capabilities, and we do that, all of that with compatibility with existing applications. So those are the value propositions that we can deliver and the pain points that we can solve. All right, so let me wrap up my presentation with a view towards the future. Today, if we walk into a data center, we see compute, we see memory. They're typically enclosed in a server enclosure, and they're networking, interconnecting them, as well interconnecting them with storage systems. And they can be primary performance-driven storage systems or flash systems, etc. And there will be capacity storage. These are the bulk, the secondary storage, DS3s, that are really handling the capacity of the data. And so that's sort of your typical stack today. We think we are on the cusp of a new transformation of the data center infrastructure, where the hardware devices will become more heterogeneous. This will appear in compute with CPUs, GPUs, FPGAs, ASICs, AI chips, etc. So it'll be various computing elements that's underneath the infrastructure, and there will be also heterogeneous memory units, including the 3D crosspoint, which is the phase change memory, as well as resistive memory and other memories to be added in addition to DRAM. And there will be a new fabric called CXL that we believe is the future, that seems to be embraced by both Intel and AMD to interconnect between these computing elements and memory elements. So this is kind of completely underneath a new new formation of the different devices. It's a more heterogeneous world. And because it's so heterogeneous, and because there's thousands of applications of top that's written already, we believe there is a software layer that can make this data center to be software defined and composable. And this is a software that can harness these computing resources, memory resources, interconnected by this new fabric, either within a server or across the servers within a few racks. And there needs to be the software to harness and orchestrate and make all these resources consumable by the applications, old and new. And so this is the virtualization layer that we think are up and coming, and big memory software belong to this category. And we are one of the first movers in this category of the big memory software. And we believe this has a potential of moving many tens of billions of dollars in IT from one area to the other. And this software tier itself will grow into a $10 billion plus market. So we are quite excited about the vision we have for this place that we're working. And more of our customers are seeing the world in the same way as well. And I think this will drive many other innovations on top of this new infrastructure that really enable a new platform to develop and deploy applications that is memory-centric and software-defined. And really the sky is the limit. And I think the future is already here. With Intel being the first one shipping the new hardware, and we being the first software vendor delivering it. And but we will not be the only ones. And I think we welcome other technology to join the space to create this brave new world. Okay, I think that's the end of my presentation, and certainly would welcome comments. If you need to find more information, please go to our website, www.memverge.com. There are links there to write to us, to ask questions. There are also requests for demos. Thank you very much.